This week we will consider three types of function fields as an example of the notions we have seen so far. The first one is the rational function field, and the second one will be elliptic, and the last one will be the hyperelliptic. And as we have seen last week, we redefined the rational function fields in terms of its genus, and depending on it contains a degree 1 divisor. And by using the Riemann space of degree 1 divisor, we conclude that there exists a rational place in the rational function field. And by checking with respect to this rational place, we consider the Riemann spaces, and we have concluded that indeed for any rational place, their corresponding Riemann spaces has trivial has proper inclusion, and we also consider the canonical divisor because we characterize it as its dimension and its degree. And canonically, if we represent our rational function field with respect to some transcendental x, and if P infinity denotes its pole divisor, we mentioned that in general the canonical divisor will be taken as minus 2p infinity. As we can check, it has dimension 0 because it has negative degree, and its degree is minus 2 because p infinity is a rational place. And moreover, if we also observe that if we have two equivalent, in general, we know that if we have two equivalent divisors, we know that they have the same degree. In the rational function field, we also observe that the other way around also hold. And finally, we consider the class group, and we conclude that this is isomorphic. It has a group, and there's a group isomorphism between the integers and the class group of the rational function field. And to complete, to be able to say more, finally, I want to consider the subfields of the rational function fields, particularly going over an example exercise, first exercise of the first chapter in the textbook. And which says that if we have a rational function field, and if we consider a function, a non-constant function, which is represented as f over g, here f and g denote the relatively prime polynomials, and indeed we will be able to compute the extension degree of k of x over k of z, and we will observe that indeed in this case the extension degree will be the maximum of the degree of the numerator f and the denominator degree of the denominator g of x. And for the notation, let me fix it, let me denote it by degree of z. So first, we know that for any algebraic function field, its expansion degree is determined by the degree of the pole divisor of this transcendental of the base field. And here, our claim is that indeed degree of the pole divisor is equal to maximum of the degree of f and g. As we also, depending on the extension degree, we also want to write the minimal polynomial of x over k of z. So first, to be able to see these facts, first let me consider the decomposition of f and g into irreducible factors. Here, pi and qj of x denote monic irreducible pairwise distinct polynomials. And we have seen that indeed it's the principal divisor of this element set. And it will be the same thing with the factorization. Degree f maybe I should write here degree f, degree g minus degree f times p infinity. And here p infinity denote the pole divisor of x as usual. And here pi and the qj denotes the corresponding places for the irreducibles generated by the irreducibles pi x and qj x. And if you consider the principal, if you write the principal divisor as a difference between its zero and pole divisor, so now our claims that depending on this decomposition and the degree of the numerator and the denominator, indeed the extension degree is the maximum of the degree of f and g. And to see that degree z infinity is equal to degree of z so to be able to prove that, we distinguish the two cases. First, we suppose that degree of f of x is strictly less than degree of g of x. And in this case, valuation of z is degree g minus degree f is strictly positive. So that means if this is strictly positive, p in infinity should be it will be a part of the zero divisor of z. In other words, zero divisor of z is equal to the summation of the pi's and some multiple of the p infinity, and pole divisor in this case will be mjqj. And if we compute the degree of the zero divisor, this is indeed the degree of g of x, and degree of degree of the pole divisor is the degree of the g of x, because degree of this qj's will be the degree of the irreducible qj's, and the degree of the zero divisor is degree of x, degree of g of x minus degree of f of x. This is indeed again degree of g of x. And since, well, by our assumption, we also know that the maximum of f and g, the maximum of the degree and degree of f and the degree of g will be degree of g of x, and this gives us the desired. So to be able to represent its minimal polynomial, let me denote this extension degree by d, and we know that the minimal polynomial of x over z should be a polynomial of degree d. And to write it, we know that we represent z as f over g, and so that means we can write 1 over z as g over f when or as the degree of f is strictly less than of degree g. And multiplying both sides by f of x with respect to this equality, we may consider the polynomial phi of t as g of t minus 1 over z f of t with coefficients from the rational function field k of z over the polynomial ring with indeterminate t. And here note that since the degree g is strictly bigger than degree of f, indeed this polynomial has degree g, so that means it has the same degree with the extension degree, and this phi of t also contains x as a root because of this equality, and indeed this gives us the irreducible polynomial of x, or more accurately minimal polynomial of x over the rational function field k of z. And in the second case, we suppose that degree f is bigger than or equal to degree of g of x. In this case, the zero divisor of z will be NIPI, sum of the NIPIs, and P infinity will be a part of the pole divisor of z. And similarly, in the first case, we can verify that the degree of the pole divisor of z is equal to degree of x, and degree of the zero divisor is equal to degree of f of x. And in this case, obviously the maximum of the degrees of f and g will be degree of x, and this gives us the desired equality. And to write its minimal polynomial, now we consider this representation, and we multiply both sides by g of x. And if we consider the polynomial ft minus z times g of t, this is again a degree f polynomial, so it is consistent with the extension degree, and it contains x as a root, so this gives us the minimal polynomial of x over k of z. And as a second part of this example, we will also conclude that when two rational function fields are essentially the same, and now we will see that if we are able to transform one variable, one transcendental x to other transcendental z with respect to these spatial fractions, here the both a and g, a and c should be non-zero. And these linear factors are relatively prime. Maybe I should write it like this. The coefficients of these linear factors satisfies this equality. And this kind of transformations also appear in the complex analysis. I couldn't remember its name, but probably it should be I couldn't remember, but it has a spatial name anyway. I tried to tell you in the discussion session. And to prove that, first, let me show the sufficient condition. If we represent that as fractions of two linear factors, we know that the extension degree of k of x over k of z is determined by what we call the degree of sets. So this is the maximum of the degrees of the denominator and the denominator. And this shows us indeed two rational functions fields are the same. And for the necessary condition, so let me suppose we have two rational function fields with respect to different transcendental. So that means it has extension degree 1 by the assumption, and indeed this also shows us the degree of the pole divisor of set is 1. Or degree of set, so that means if we write it set as f over g, maximum f and degree, maximum of degree f and g will be 1. So this is only possible when f and g are the linear factors. With non-zero coefficients. And they are also relatively prime. And under this condition, we can see that indeed this implies B over A is different from D over C. So that means AD minus BC is also non-zero. And finally, indeed, we also know that thanks to what is called the Lyros theorem, for every subfield A, which contains the full constant field k of x and is a subfield of the rational function field, then thanks to this theorem, we can also say the existence of a function. This will able to represent this subfield as a simple extension with respect to transcendental z, or simply K of Z. However, its proof requires to work with the extensions of the algebraic functional fields. So this is why, in general, it is presented in chapter 3. So in the next video, by following the more or less the same structure, we try to go over the elliptic function fields.